Okay. Okay, what's up? Yeah. Whoa. What's up? Okay. Okay. In this video, I gonna talk to I gonna talk about Schrödinger equation for kids. And first, I tell you, I tell you summary of Schrödinger equation, and then I tell you three things about time independent version. What time independent version into interpretation of wave function references. Let's start. Okay, the Schrödinger equation is different equation, a type of a type of equation that involves an unknown function rather than unknown number. That forms the basis of quantum mechanics, one of the most accurate theories of how subatomic particles behave. It is a mathematical equation that was thought of by Erwin Schrödinger in 1925. It defines a free function of the particle or system group of particle which has a certain value at every point in space for every given time. These values have no physical meaning. In fact, they are mathematically complex. Yet the wave function contains all information that can be known about a particle or system. This information can be found by mathematically manipulating the wave function to return their values relating to physical properties such as position, momentum, energy, etc. The wave function can be thought of as a particle of how this particle or system acts with time, and it describes it as free as possible. The wave function can be in number of different states at once, and so particle may have many different positions, energies, and varieties or other physical properties, at the same time. However, when one of these properties is measured, it has only one specific value, which cannot be definitely predicted. And the wave function is therefore in just one specific state. This is called wave function crepes, and seems to be caused by the actual observation or measurement. The ex, the exact cause and interpretation of wave function crepes is still widely debated in the scientific community. For one particle that only moves in one direction in space, the Schrödinger equation looks like is square root L minus 1 is the reduced Planck's constant is time is position. It's the wave function, and it's the potential energy, and as yet not chosen function position. The left hand side is equivalent to the Hamiltonian energy operator acting on. Okay, it's summary. Next, I tell you about some three things. The invented first the invented version start assuming that the wave function is separable, i.e., assuming the function of two variable can be written as a product of two different functions of a single variable. Then, using standard mathematical techniques or partial differential equation, it can be shown that the wave equation can be rewritten as two distinct differential equations. where the first equation is solely dependent on time and the second equation depends only on position and where it's just a number. The first equation can be solved immediately to give in where is error number. Solutions of the second equations depend on the potential energy function and so cannot be solved until this function it's given. It can be shown using quantum mechanics that that the number is actually the energy of the system. So this separable wave functions describe systems of constant energy since energy is constant in many important physical systems, for example an electron and an atom. And the second equation of the set separated differential equations presented above is often used. The the equation is known as the time-independent Schrödinger equation as it does not involve. Okay, these are time-independent version. Next, I talk to you interpretation of the wave function, Born interpretation. Uh, there are many physical interpretations of wave function, and a few of the reading ideas will be considered here. The main idea uh, called the Born probability interpretation, named after physicist Max Born, comes from the simple idea that the wave function is square integrable, i.e. This rather simple formula has great physical information. Born hypothesized that the above integral determines that particle exists somewhere in space. But how can we find it? We use the integral, whereas the probability of finding the particle in the region from two. In other words, all that can be known advanced about particle in general probabilities, averages, and other statistical equations associating with its physical quantities, position, momentum, etc. Basically, this is the Born interpretation. We so I'm sorry to explain that we I told you I told you to I tell you references. It's not it's I we don't we don't need it, and so we keep to read comprehension and interruption. Okay. An extension of the above ideas can be made since the Born interpretation says that the actual position particle cannot be known. We can derive the following: if a solution to the wave equation, then the superposition of those solution i.e. Is also a solution. This implies then that particle exists in every possible position. When the observer comes and measures the position of the particle, then the superposition is reduced to a single possible wave function. This idea that a particle's position cannot exactly be known, and that particle exists in multiple positions, similar uh, similar tangentially gives rise to the uncertainty principle. The mathematical uh, formulation of this principle can be given by where is the century in position and is the century in momentum. This principle can be mathematically de- de- derived from the Fourier transforms between momentum and position and defined by quantum mechanics, but we will not derive it in this article. Okay, third, I tell you other interpretation. There are various other interpretations such as many world interpretation and quantum determinism. Okay, I tell you all things about Schrödinger equation. In this video, I finished it, and thank you for watching this video. Have a good quantum uh, physics day. See you next time. Goodbye.